Good afternoon. During the lecture today, I will present the notion of intrinsic distance and the exponential map. So let's start by this definition. Let S be a connected regular surface, then the intrinsic distance function of S, denoted by D, is a map defined on S times S with real values, is defined as follows. The intrinsic distance of P to Q is the infimum of the length of gamma, where gamma is a piecewise regular curve in S from P to Q for all P, Q in S. The first remark I will make is the following. The value dpq is finite. Let's prove it. We will show that two points in S can always be joined by a smooth curve. This means that the set of curves gamma which join P to Q and they are which are piecewise regular is non-empty. Okay, in order to prove that this is true, I need some preliminary material. So let's consider preliminary material. Let's consider the map alpha t defined by e power minus 1 over t if t is positive and 0 if t is non-positive. This is a map with values in 0, 1, and it is possible to prove that it is monotonic of class infinity, so this means it is smooth, and alpha t is 0 if and only if t is non-positive. The graph of this function is the following. Like this. It is 0 for t non-positive, and it tends to 1 as t tends to infinity. Now let's consider the function beta, defined this way: alpha of b minus t divided by alpha of b minus t plus alpha of t minus a, where a, b are real numbers with a is more than b. Beta is a map with values in 0, 1, smooth, so of class infinity, and it's possible to prove that beta t is 1 if and only if t is smaller or equal to a, and beta t is 0 if and only if t is larger or equal to b. So, for example, if we choose a to be -1 and b to be 1, then the graph of beta looks like approximately like this. Now that I introduced the map beta, I can state this lemma. Let sigma and tau be two smooth curves with sigma 1 equal tau at 0. Then there exists a curve sigma star tau defined on 0, 1 with values in R3, smooth such that sigma star tau restricted to 0, 1/2 is a new parametrization of sigma. Sigma star tau restricted to 1/2 1 is a new parametrization of tau. Moreover, if tau 1 is equal to sigma 0, then sigma star tau is a smooth closed curve. Okay, let's write down the sketch of the proof. So let beta define on R with values in 0, 1 the C infinity, the smooth regular curve introduced before, choose A to be 0 and B to be 1. Then sigma composed with beta I prefer to correct and replace this word by function, because we don't need a curve here, sorry. So then sigma composed with beta is a reparameterization of sigma whose derivatives are all 0 in 0 and 1. The curve sigma star tau is defined by the following formula. This is a regular curve the reason why it is smooth is that in the joining point corresponding to t equal 1/2, all the derivatives are 0, and the smoothness at other points follows from the smoothness of sigma and tau and beta. And this curve has all the properties presented in the statement of the lemma. remember that our goal is to prove that uh, 2 points in S can be joined by a smooth regular curve. In order to prove that this is true, I need this definition. A subset X over 3 is locally connected by smooth arcs if every point X in capital X has a neighborhood W in R3 such that for all Y in W intersection X there exists a curve, a smooth curve sigma with support with trace contained next such that sigma 0 is X, sigma 1 is Y. So this definition says that a subset is locally connected if for each point small x there exists a neighborhood made of point y for which there exists a curve which joins x to y. Now I want to prove this statement here. This is a consequence of the following result. So let's consider a subset over 3. which is connected and locally connected by smooth arcs. Then for all x and y in capital X, there exists a curve sigma a smooth curve regular curve sigma such that the trace is contained in X and sigma 0 is X, sigma 1 is Y. Okay, idea of the proof. So let's introduce on X an equivalence relation tilde this is defined by this X is equivalent to Y if and only if there exists a curve a smooth regular curve with trace contained in X and such that sigma 0 is X, sigma 1 is Y. Okay, the lemma I proved before implies this is an equivalence relation. Um, now we use the fact that we have local connectivity, and this implies that the equivalence classes are open. So this says that the classes of equivalence form an open partition of X. Now we use the fact that X is connected. And this implies that there is only one equivalence class. And this is the end of the proof. Why? Because if there is only one equivalence class, this means that any point of X can be joined to the point small x. The reason why this lemma, this proposition can be used in our case is that it's possible to prove that a connected regular surface is locally connected by smooth arcs. Okay, now what I want to do is to prove lemma 5.10, which says that if S is a connected regular surface, then for all P, Q, R in S, we have one intrinsic distance of P to Q is a non-negative, and the equality holds if and only if P coincide with Q, 2 dpq is equal to dqp, 3 dpq is smaller or equal to dpr plus drq. In other terms, the intrinsic distance is a distance. Okay, let's see the proof of this. The property 1 and 2, essentially they follow from the definition. Why? This is true because the intrinsic existence is defined as the infimum of positive numbers, and the reason why you can have equality if and only if P is equal to Q is that when P is equal to Q, you can take the regular curve, which is a constant. I mean, you can join P to itself using a constant map. The reason why 2 is true is that if you have a curve joining P to Q, then you can change the parameterization and you can create a new curve which joins Q to P. So essentially it remains to prove only the property number 3. So suppose that sigma is a piecewise regular curve piecewise smooth regular curve joining P to Q, and suppose that tau is a piecewise regular smooth regular curve joining sorry, I made made a typo because I need this to be R, joining R to Q. Then sigma star tau is a curve joining P to Q and satisfying the fact that the length is equal to the length of sigma plus the length of tau. So if now we take the infimum on sigma and tau, this implies that the intrinsic distance of P to Q will be equal to intrinsic distance of P to R plus intrinsic distance of R to Q. And finally, how to prove that dPQ is positive if P is not Q. This can be proved using the fact that dPQ is larger or equal than the length of the vector P minus Q. And this is the end of the proof. Now let's consider one example. So let this be the punctured plane R2 minus the origin, and let P be the point of coordinates -1, 0, and Q be the point of coordinate 1, 0. Let's ask ourselves what is the intrinsic distance of P to Q. So this is the point P, this is the point Q, and this is the origin. According to the definition, we have to consider all the piecewise regular curves joining P to Q. So for example, you can take curves like this, and then you have to take the infimum. So for example, if you take all the curves having the same shape, but with this arc of circle having a radius which tends to 0, you will find that the intrinsic distance of P to Q is exactly 2, but this is not a minimum, because the origin is omitted. This would be a minimum, that is an infimum which is achieved only if we could consider straight lines passing through the origin, but it's not the case. Our next goal is to ask ourselves and find the answer of the following question. What is the relationship between geodesics and the shortest curves between two points? In other terms, we want to know if a geodesic is the shortest curve between 2 points, and vice versa if the shortest curve between 2 points is a geodesic. In the case of the plane, the answer to these two questions is yes. It's not true for a surface. I need the following definitions. So let S be a regular surface, and gamma a piecewise regular curve in S. 1. Suppose that I is a closed interval like this, that is compact. Gamma is called minimizing. If the length of gamma coincide with the distance, the intrinsic distance of gamma A to gamma B. And gamma is called locally minimizing if additionally excuse me, it's not locally minimizing, but it's uniquely minimizing. We will see in a moment the definition of locally minimizing. Okay, so it's uniquely minimizing if additionally every other piecewise regular curve in S from gamma A to gamma B with the same length as gamma must have the same trace as gamma So this is the definition of minimizing curve and uniquely minimizing curve if the domain I is a closed interval. This is not always the case. So we have part 2 of the definition. For general I, gamma is called minimizing or uniquely minimizing if the restriction of gamma to every compact subinterval of I has this property. And the last definition I want to present is the definition of locally minimizing. So for general I, gamma is called locally minimizing if for every t0 in I, sorry, in the interior of I, there exists a compact subinterval of I with the interior of J, where J is the subinterval containing T0 restricted to which gamma is minimizing as defined in 1. So locally minimizing means that once you choose a point in the interior of your interval of definition of the curve, then you can find a compact subinterval containing the point you chose, such that the restriction of your curve to this subinterval is minimizing. In order to answer the question I presented before, I need to introduce the notion of exponential map. Definition. So as usual, we have a regular surface and we fix a point on this surface choose the largest possible epsilon equal epsilon of P1 possibly infinite, which is guaranteed by proposition 5.3. This was a proposition about the existence of geodesic with initial point P. Then set B epsilon equal the disk in TPS of open disk of radius epsilon. In the case when epsilon is plus infinity, then we have that p epsilon is TPS in this case. The exponential map of S at P is the function denoted by x per p defined on B epsilon with values in S, defined as follows: x at P evaluated at V is the point P if V is 0, and gamma V1 V in B epsilon V different from the 0 vector. Where gamma V denotes the geodesic in S with an initial velocity P, initial position equal to V and initial velocity equal to V. We can use the equation (5.1) gamma R U T equal gamma U R T, where R is a real number, for writing down an alternative description of the exponential map. So if U in TPS has a unit length, and zeros more than R more than epsilon, then we can write x p of RU is equal to gamma UR. Clearly, this formula follows from this one. Why? Because any vector V in B epsilon can be written as R times a unit length vector. For example, V of non-unit length can be written as length of V times V over length of V. So this will play the role of U and this will play the role of R. And if you use this formula with t equal to 1, then you get immediately that xp of ru is gamma u of r. So what this definition says, that exp pru, this is point in S, reached by traveling a time r along the unit speed geodesic gamma u starting at p in the direction u. Please observe that if you travel along a geodesic which has a unit speed, then you have that time r implies that you travel a distance equal to r. So in other terms, the point exp pru is located at a distance r from p. Why? Because this is a geodesic having a unit speed. Let's try to make a picture. So suppose that this is my surface S. This is the point P. This is the translation of TPS so that the origin coincides with P. So I will write P plus TPS. And suppose that this is the vector U. Then suppose that this is the length of R. Then what is exp PRU is the point that we reach if we move along a geodesic starting at P with the initial direction given to you. For example, this point here. And from this picture, you understand that the exponential map sends lines to geodesics. Why? Because if r varies between 0 and epsilon, you send segments of line to segment of geodesics. So in order to be more precise, I can write that indeed the line T is sent to TU. This is a line in P plus TPS. Is mapped to the geodesic T gamma ut. So line in TPS in S. Okay, now let's prove some property of the exponential map. So there exists epsilon positive, possibly smaller than the value of previous definition, such that the exponential map at P is a diffeomorphism from B epsilon onto O epsilon of P, which is defined to be exp at P of B epsilon. O epsilon of P, this is called normal neighborhood of P in S of radius epsilon. Okay, let's prove this result. The idea of the proof is essentially the following. Use the inverse function theorem for surfaces. After proving that the derivative of the exponential map at p at 0, where 0 means the 0 vector, defined between these two tangent spaces, is invertible. Why this is enough? This is enough because we already know that the exponential map is smooth. The reason why it's smooth is that we have that the smoothness of exp p follows from proposition 5.3, the one which says that once you fix a point and an initial velocity vector, then there exists a geodesic at least on a small interval. This proposition says also that the geodesic is a smooth function of the initial point of the initial vector and the parameter t. So this implies that the exponential map is smooth because since the geodesic is smooth with respect to the initial velocity vector, then the exponential map will be a smooth map with respect to the vector v of TPS you chose. So it remains to prove that its inverse is smooth. And this is the fact that you prove using the inverse function theorem. Okay, now let's compute the derivative of the exponential map at 0. How to compute the differential of this map? This looks complicated, but remember that we have a tool. When you want to compute the derivative of a function in a certain direction, you have to choose a curve having that direction, the direction you chose as initial direction, and then you compute the derivative of the composite function that you get evaluating the function of which you want to compute the derivative along that curve. So in other terms, consider the curve tau t equal TV. This is a curve in this is a curve in TPS. Then what is the derivative of exp p at 0 applied to v? This is the derivative with respect to t of exp composed with tau at t equal to 0. But this is ddt of gamma tv at 1 evaluated at t equal to 0. But this is equal to ddt of gamma vt evaluated at t equal to 0. That is gamma v prime 0. That is v. So we found that the derivative of exp p at 0 evaluated at v is v. So it is the identity map implies invertible now we can use the inverse function theorem to get that there exists a neighborhood of 0 in TPS such that the inverse of the exponential map is smooth. If we combine this fact with the smoothness of the exponential map, then we have that exp p is a diffeomorphism on a small neighborhood of 0 in TPS. I think it's a good point where to stop. So that's all for today. Thank you for your attention.